Sound feels simple because we live inside it. We grow up surrounded by it, so it feels almost primitive compared to light or atoms. But sound is one of the most violent things matter can experience. At its heart, sound is not noise, it is matter being shoved, pulled, and stressed rhythmically. When you speak, the air near your mouth is physically compressed and stretched. Those tiny mechanical disturbances move outward, passing the stress from one molecule to the next like an organized microscopic panic. Nothing travels with the sound except energy and pressure. No particle makes the journey. Matter only agrees, briefly, to be disturbed. The reason sound feels weak to us is because everyday sounds barely nudge matter from its resting state. Normal speech changes air pressure by less than 1/10,000th of atmospheric pressure. Even a loud concert barely pushes air molecules a few nanometers from where they want to be. But this gentleness is misleading. Sound is fundamentally limited not by our ears, but by how much stress matter itself can tolerate, and matter is far less forgiving than it looks. This is why sound needs a medium and why space is silent, not because it is calm, but because there is nothing to compress, nothing to pull back. Sound is not a thing that exists on its own. It is a behavior matter performs under stress. To make sound louder, you don't add more waves, you increase the pressure swing. Louder sound means denser compressions and deeper rarefactions. This is where the idea of a loudest possible sound quietly emerges. Rarefaction means lowering pressure, but pressure cannot go below zero. You cannot pull matter apart beyond vacuum. When a sound wave tries to create a region with negative pressure, the wave simply breaks. Physics refuses to cooperate. This happens at around 194 decibels in air. That number is not chosen by biology or by human ears. It comes from atmospheric pressure itself. At this point, the low-pressure part of the wave would require air to have less than zero pressure, an impossibility. The wave collapses into a shock front. From that moment on, it is no longer sound in the physical sense, it is a shock wave. Here's a strange and unintuitive fact. No explosion, no matter how powerful, can produce a louder sound than this in air. Nuclear weapons do not break this limit. Meteor impacts do not break it. They do not create louder sound, they create more shock spread over a larger area. Loudness hits a ceiling, destruction does not. Another weird consequence, two 194 decibel sounds cannot combine to make something louder. There is no stacking beyond the limit. The universe simply refuses to support it. Different materials change the number, but not the rule. Water allows higher pressure swings than air, so the loudest possible sound in water is higher. Solids can tolerate even more stress, which is why ultrasonic waves can shatter metal internally without ever sounding loud to us. But the same boundary exists everywhere. Once the material can no longer respond elastically, once molecules cannot spring back, sound ends and shock begins. This is why the loudest sound inside Earth during earthquakes is not really sound. Seismic waves are slow, massive stress rearrangements, not audible pressure oscillations. It's also why the sun, despite its violence, does not roar. Inside stars, pressure disturbances become plasma oscillations and shock fronts, not sound as we define it. And here's a deeply unsettling fact. If you somehow survived exposure to a sound approaching the physical limit, you would not hear it. Your eardrum would be destroyed before vibration could even occur. Loudness stops being sensory long before it stops being physical. At extreme amplitudes, sound stops being information and becomes damage. When sound amplitudes become large, the equations we teach for waves quietly fail. Linear acoustics assumes that pressure changes are small and symmetric, but near the loudness limit, symmetry collapses. Compression travels faster than rarefaction. The crest catches up with the trough. What began as a smooth oscillation sharpens into a vertical wall of pressure. This is not a metaphor. Mathematically, the waveform develops a discontinuity. A shock is born. This is nonlinear acoustics, and it tells us something unsettling. Nature does not like smoothness at extremes. Loud sound destroys its own wave shape. The medium heats locally, entropy increases, and energy leaks into irreversible processes. Sound ceases to be a clean carrier of information and becomes dissipation. That is why the loudest sound is not just a biological limit or a materials limit, it's a thermodynamic one. In laboratories, researchers have approached this regime using focused ultrasound and gas dynamic shock tubes. As amplitude increases, higher harmonics appear spontaneously. The sound generates new frequencies out of nothing but stress. This is why extremely loud sound becomes harsh and distorted. It is literally manufacturing frequencies as it propagates. By the time you reach the physical ceiling, the concept of a single frequency has lost meaning altogether. One strange experimental fact: in high-intensity ultrasound, sound can heat matter faster than flames. It can create cavitation bubbles that collapse violently, producing temperatures of thousands of Kelvin for microseconds. In these collapses, light is emitted, a phenomenon called sonoluminescence. Sound, under the right conditions, produces light. This is not science fiction, it is repeatable laboratory physics. Now we need to address the question people always ask: what about sound and space? The simple answer is there is none, but the deeper answer is more interesting. Sound requires a medium with elasticity, something that resists compression and pulls back. Empty space does not resist, but plasma does, gas does, dust clouds do. Inside galaxy clusters, pressure waves propagate through thin plasma over millions of light years. These waves are sometimes casually described as sounds, but they are closer to colossal pressure oscillations than anything your ear could interpret. NASA once famously translated pressure oscillations in a galaxy cluster into audible frequencies. This was not sound traveling through vacuum, it was data sonified for human perception. The universe did not make a noise, we assigned it one. And here's the key point. Even in these cosmic plasmas, the same rule holds. There is still a maximum compressibility. There is still a point where waves steepen into shocks. Supernova remnants are not loud sounds, they are shock fronts tearing through interstellar gas. The universe does not shout, it breaks. At the deepest level, the loudest sound limit is a statement about energy density. Sound packs energy into pressure. Push too much energy into too small a volume, and matter changes phase. Gases ionize, solids fracture, plasmas reorganize. Sound is only possible while matter agrees to oscillate around equilibrium. Once equilibrium is lost, oscillation dies. This is why the loudest possible sound is not set by decibels alone, but by equations of state, the relationship between pressure, density, and temperature. In neutron star matter, where compressibility is almost zero, pressure disturbances behave nothing like sound. In such environments, information travels through entirely different modes. Sound, as a concept, becomes meaningless. So the loudest sound the universe allows is not a universal number, it is a universal principle. There is a boundary where oscillation gives way to rupture. And that boundary appears everywhere, in air, in oceans, in stars, and in the mathematics itself. This brings us to the quiet philosophical punchline. Sound feels ephemeral, it vanishes as soon as it is made, but at its extreme, sound reveals something permanent. The universe enforces restraint, not through gentleness, but through failure. When pushed too hard, nature does not respond louder, it responds differently. There is no infinite volume, no ultimate scream, only a transition from order to shock. When sound crosses into the shock regime, something subtle but profound happens. Information flow changes direction. In ordinary sound, the medium responds locally and reversibly. Molecules compress, then return. Cause and effect are smooth. But in shocks, dissipation dominates. Energy is no longer stored and returned, it is lost to heat, ionization, and irreversible rearrangement. This means that beyond a certain loudness, sound cannot faithfully carry information. The universe imposes not just a loudness limit, but a communication limit. This is why extreme sound is useless for signaling. No matter how much energy you add, you cannot encode more detail. The wave destroys its own structure faster than it can propagate. In technical terms, entropy production overwhelms coherence. Loudness becomes noise in the most literal thermodynamic sense. This connects directly to research in nonlinear wave theory. Mathematically, sound waves are solutions to conservation equations. As amplitude grows, these equations develop singularities, points where derivatives diverge. Physicists do not interpret this as nature going infinite. They interpret it as the theory telling you it has crossed a boundary. Nature is warning you the assumptions behind sound are no longer valid. There is even a stranger consequence. At sufficiently high intensities, sound can change the speed at which it travels. Normally, sound speed depends on the medium, not the wave itself. But in nonlinear acoustics, the wave modifies the medium as it passes. Compressed regions become hotter and stiffer, allowing the wave to move faster there. This feedback is what causes steepening. The wave accelerates itself into destruction.
This is rare in physics. Most waves do not self-destruct by amplifying their own propagation speed. Sound does. In high-energy acoustics labs, this effect is used deliberately. Focused ultrasound can generate localized pressures strong enough to tear apart cells, fragment kidney stones, or open the blood-brain barrier temporarily. These are not loud sounds in the everyday sense. They are controlled violations of elastic response. Medicine quietly uses the same physics that defines the loudest sound limit. Now consider this unsettling fact. Pressure and gravity are deeply connected. In Einstein's equations, pressure contributes to gravity just like mass energy. At extreme levels, a sufficiently intense pressure wave contributes to space-time curvature. This does not mean sound can make a black hole, but it does mean that the boundary between acoustics and gravitation is not conceptual, it is mathematical. In relativistic fluid dynamics, shock waves are treated as discontinuities in space-time stress energy. Sound ceases to be a vibration and becomes a feature of geometry. At that depth, asking how loud something is stops making sense entirely. This is why in astrophysics we never talk about loudness. We talk about Mach numbers, compression ratios, and entropy jumps. The language changes because the phenomenon has crossed categories. Another weird but true fact, the loudest sound-like events in the universe are invisible to ears, not because space is silent, but because human hearing evolved for linear acoustics. Our ears assume smooth oscillations. They cannot interpret shocks. To an ear, a shock wave is not loud, it is destructive. This is why explosions do not sound like louder noises. They sound like events. Your auditory system saturates long before physics does. At the deepest theoretical level, sound exists only because matter has a stable equilibrium state. Remove equilibrium, remove sound. This ties the loudest sound limit to phase transitions. Near critical points, where matter is about to change phase, compressibility diverges and sound speed collapses. Sound becomes sluggish, distorted, and unstable. In such conditions, even small disturbances can trigger shocks. So paradoxically, near instability, quiet sounds become dangerous. This has been observed experimentally in fluids near critical temperature, where sound attenuation skyrockets. The medium stops wanting to oscillate, it prefers to transform. And here is a fact that feels philosophical, but is purely physical. Sound is possible only in worlds that are forgiving. The loudest sound limit marks the edge of forgiveness. Beyond it, matter refuses to oscillate. It chooses rupture, heat, ionization, or reconfiguration instead. The universe does not allow infinite stress to remain rhythmic. At sufficiently extreme pressures, the distinction between a sound wave and a material deformation blurs completely. The wave no longer rides on matter, it rewrites the material as it passes. This is why the deepest studies of intense acoustics borrow tools from fracture mechanics and phase transition theory. The question is no longer how large is the pressure oscillation, but what microscopic pathways exist for the material to escape oscillation. Every material has escape routes. Sound finds them. There is a subtle hierarchy hidden here. Elastic response is the most orderly. Plastic response comes next. Fracture follows that. Ionization follows that. Each step represents a deeper failure of reversibility. Loud sound pushes matter down this hierarchy. The louder it gets, the fewer reversible degrees of freedom remain. In that sense, loudness measures how close matter is to abandoning memory. At even higher energy densities, acoustic disturbances couple directly to chemical reactions. Pressure spikes alter reaction rates by reshaping potential energy landscapes. Bonds that would never break thermally can be forced apart mechanically. This is not metaphorical chemistry. It is studied under the name mechanochemistry. Sound becomes a catalyst, not by heating, but by distorting the geometry of molecules themselves. So loud sound does not just destroy, it chooses which reactions occur. In fluids approaching relativistic regimes, pressure and energy density become comparable. The inertia of pressure can no longer be ignored. Momentum is carried not just by mass flow, but stress itself. In these conditions, the language of acoustics disappears entirely. What remains are conservation laws written in space-time form. Waves are no longer oscillations of density, but propagating discontinuities in stress energy. Here, the loudest sound is defined by how steeply stress energy can jump while remaining causal. The limit is no longer atmospheric, it is geometric. One consequence is deeply counterintuitive. In extreme regimes, adding energy to a pressure wave can slow it down. Energy goes into rearranging internal degrees of freedom instead of propagation. This happens near phase boundaries and critical points. The wave becomes heavy. It carries too much internal complexity to move cleanly. Loudness collapses under its own richness.
Even more strangely, the medium can begin to store fragments of the wave. Memory effects appear. After the disturbance passes, residual stresses and altered microstates persist. Later waves interact with these remnants. The medium remembers being shouted at. In this way, sound history becomes encoded into matter. At very small scales, where continuum descriptions fail entirely, sound-like disturbances are better understood as correlated momentum transfers. The idea of a smooth wave dissolves into a choreography of collisions. There is no crest or trough, only probability distributions evolving in time. Loudness becomes a statement about how far from equilibrium these distributions are driven. This is why the loudest sound cannot be sharp at the smallest scales. Sharpness requires coherence. Coherence is the first casualty. There is an echo here of a broader pattern in physics. Every system tolerates small departures from equilibrium gracefully. Push harder and linear response fails. Push harder still, and the very variables you were using lose meaning. Loud sound is simply one of the clearest demonstrations of this universal structure. The universe is not fragile, it is layered. Each layer gives way to another when abused. In that sense, the loudest sound is not a sound at all. It is a boundary between descriptions. On one side, waves. On the other, shocks, fractures, reactions, entropy, geometry. The transition is not marked by a bang, but by the quiet disappearance of oscillation as a valid idea. And still, there is more depth beneath even that. There is an even deeper way to see the loudest sound limit, as a failure of symmetry. Ordinary sound relies on time reversal symmetry. Run the wave backward and nothing looks wrong. Molecules retrace their steps. Energy returns. But shocks are asymmetric. You cannot run a shock backward and recover a sound wave. The equations allow the forward process and forbid the reverse. Loudness at its extreme breaks symmetry itself. This is why shock formation is one of the cleanest macroscopic demonstrations of the arrow of irreversibility in physics. You do not need cosmology or black holes. You can see it in air. At high amplitudes, sound also exposes a hidden hierarchy of speeds inside matter. There is not just the speed of sound. There are speeds of compression, speeds of heat transport, speeds of defect motion, speeds of chemical rearrangement. When sound is weak, it stays below all of them. When sound is pushed toward its limit, it collides with them. Energy diverts sideways into channels that were invisible before. This is why extreme acoustics looks messy. It is not chaos, it is competition. There is a remarkable parallel with turbulence. As sound grows stronger, it begins to cascade energy across scales. Large, coherent motion feeds smaller, incoherent motion. Eventually, energy reaches scales where viscosity dominates and motion dies into heat. Loud sound accelerates that cascade. At the limit, sound is swallowed by its own turbulence. In this sense, the loudest sound is the fastest way to destroy sound. Some theorists describe this as a kind of acoustic censorship. Just as certain theories suggest that singularities are hidden behind horizons, acoustics hides its own infinities behind shocks. You never observe infinite gradients, you observe a breakdown that prevents them. Nature does not allow naked infinities, even in air. Even more deeply, sound's limit reflects a universal rule. No signal can remain linear while carrying arbitrarily large energy density. Linear behavior is a privilege of weakness. Strength demands nonlinearity. Nonlinearity demands loss. Sound obeys the same logic as every other interaction in the universe. Push hard enough, and the description you trusted betrays you. At extreme depths, the loudest sound problem stops being about waves and becomes about the stability of laws. Sound exists only because matter obeys local equilibrium thermodynamics. That is an assumption, not a guarantee. Push hard enough, and equilibrium ceases to be locally meaningful. Temperature, pressure, and density stop being well-defined at a point. They smear across scales. The very variables that define sound dissolve. This is profound. The loudest sound limit is not imposed on sound. It is imposed by the collapse of the concept of sound itself. There is a deep analogy here with renormalization in physics. At low energies, you describe matter with simple parameters. At higher energies, new degrees of freedom appear. Loud sound is a renormalization flow in real space. As amplitude increases, the effective description flows away from acoustics toward hydrodynamics, then toward kinetic theory, then toward microscopic chaos. Each step erases simplicity. Another strange truth: the loudest sound limit is inseparable from causality even in non-relativistic media. When gradients become too steep, neighboring regions can no longer agree on cause and effect smoothly. Information outruns local relaxation. The medium cannot decide how to respond quickly enough. Shocks appear not because of violence, but because agreement fails. Sound is collective consent. Loud sound is collective disagreement. In mathematical terms, this appears as hyperbolic equations developing multi-valued solutions. The physics forbids this, so nature resolves it with discontinuities. The shock is not an object, it is a rule enforcement mechanism, a way for reality to remain single-valued when equations threaten ambiguity. This is one of the rare places where mathematics visibly flinches.
At still deeper levels, the limit of sound reflects a universal tension between continuity and discreteness. Sound assumes continuity, smooth fields, smooth waves. Matter is discrete. Molecules collide, bonds snap. At small disturbances, discreteness averages out. At extreme disturbances, discreteness asserts itself violently. The loudest sound is the point where discreteness wins. Even quantum mechanics cannot rescue sound beyond this boundary. Quantizing vibrations gives phonons, but phonons interact. At high densities, they scatter, merge, decay. Coherence is destroyed by interaction. The loudest sound is not blocked by quantum limits, it is erased by quantum complexity. More quanta does not mean clearer waves, it means faster thermalization. There is an eerie universality here. The same structure appears in light, gravity, fluids, and information theory. Systems allow small signals to propagate cleanly. Large signals trigger nonlinearities. Nonlinearities trigger dissipation. Dissipation destroys signal identity. Sound is just the most visceral example because we live inside it. At this depth, loudness becomes a proxy for how close matter is to surrendering predictability. Below the limit, the future is calculable. Above it, statistics replace trajectories. You no longer ask what will happen, only what is likely. Sound crosses from determinism to probability. And then there is the quietest and strangest insight of all. The loudest sound is not loud because it is powerful. It is loud because it is the last place where oscillation survives at all. Beyond that, the universe does not answer with noise, it answers with transformation. And even here, this is not the bottom. At even greater depth, the loudest sound limit can be seen as a boundary between description and reality. Sound is a description, a way humans compress an enormous number of microscopic events into a single elegant story. Pressure up, pressure down, oscillation, frequency. But descriptions survive only while the world. At still deeper levels, the limit of sound reflects a universal tension between continuity and discreteness. Sound assumes continuity, smooth fields, smooth waves. Matter is discrete. Molecules collide, bonds snap. At small disturbances, discreteness averages out. At extreme disturbances, discreteness asserts itself violently. The loudest sound is the point where discreteness wins. Even quantum mechanics cannot rescue sound beyond this boundary. Quantizing vibrations gives phonons, but phonons interact. At high densities, they scatter, merge, decay. Coherence is destroyed by interaction. The loudest sound is not blocked by quantum limits, it is erased by quantum complexity. More quanta does not mean clearer waves, it means faster thermalization. There is an eerie universality here. The same structure appears in light, gravity, fluids, and information theory. Systems allow small signals to propagate cleanly. Large signals trigger nonlinearities. Nonlinearities trigger dissipation. Dissipation destroys signal identity. Sound is just the most visceral example because we live inside it. At this depth, loudness becomes a proxy for how close matter is to surrendering predictability. Below the limit, the future is calculable. Above it, statistics replace trajectories. You no longer ask what will happen, only what is likely. Sound crosses from determinism to probability. And then there is the quietest and strangest insight of all. The loudest sound is not loud because it is powerful. It is loud because it is the last place where oscillation survives at all. Beyond that, the universe does not answer with noise, it answers with transformation. And even here, this is not the bottom. At even greater depth, the loudest sound limit can be seen as a boundary between description and reality. Sound is a description, a way humans compress an enormous number of microscopic events into a single elegant story. Pressure up, pressure down, oscillation, frequency. But descriptions survive only while the world cooperates. When the disturbance grows too intense, reality stops fitting inside the story. The story breaks first, not the world. This is why physicists do not say sound fails. They say the acoustic approximation fails. Reality keeps going. Our language does not. There is a hidden informational aspect here. Sound is an ordered flow of information through matter. Each oscillation tells the next layer how to move. At small amplitudes, information travels cleanly. At extreme amplitudes, information density becomes too high. Neighboring regions receive contradictory instructions before they can respond. Information overload produces shock. So the loudest sound is also an information bottleneck. Matter cannot process stress instructions faster than its internal relaxation times. When input exceeds processing capacity, coherence collapses. This is eerily similar to what happens in computation, biology, and even cognition. Go deeper still, and you find that sound's limit is tied to response time. Every material has characteristic timescales: collision times, vibration times, diffusion times. Sound assumes that these are short compared to the wave period. Loud sound violates this assumption locally. The wave demands a response faster than the medium can physically deliver. The shock is the medium saying, "I cannot respond that fast." At the most microscopic scale, sound interrogates the irreversibility built into nature. Collisions are never perfectly elastic. Energy leaks into internal modes. Every oscillation bleeds a little order into heat. Loud sound accelerates this leakage catastrophically. The louder the sound, the faster the drain.
In this view, the loudest sound is simply the fastest way to erase oscillation from existence. There is also a geometric interpretation. In space-time diagrams of fluid motion, sound waves are smooth curves. Shocks are folds. When waves become too steep, the geometry of trajectories overlaps. Multiple futures try to occupy the same point. The shock resolves the conflict by selecting one outcome and discarding the others as entropy. Geometry enforces loudness limits without asking permission. Even deeper, the loudest sound limit is connected to why nature prefers gradients over jumps, until it doesn't. Smoothness is energetically cheap up to a point. Beyond that, sharp transitions become cheaper than continuous ones. Shocks are not failures, they are energy minimizers under extreme constraints. So the universe is not preventing loud sound out of fragility, it is choosing efficiency. This perspective reveals something unsettling. If matter were perfectly forgiving, sound could grow without bound. The fact that it cannot tells us something intimate about the grain of reality. Reality is stiff. It resists being told what to do too quickly, too strongly, too precisely. Sound reaches the edge of obedience. At this depth, loudness is no longer about ears, air, or decibels. It is about how far order can be imposed before nature switches strategies. Oscillation is one strategy. Shock is another. Transformation is another still. Sound is merely the gentlest strategy. And beneath even this, there is a quiet echo of a universal pattern. Every physical theory contains its own undoing. Push it hard enough, and it reveals the doorway to the next theory. Sound pushed to its extreme does not become infinite. It becomes something else. At the most advanced level, the loudest sound limit is best understood through hyperbolic conservation laws. Sound waves are solutions to these laws under the assumption of smoothness. But hyperbolic systems generically evolve smooth initial conditions into discontinuities. This is not a flaw of sound. It is a mathematical inevitability. Given enough amplitude, steepening must occur. Shock formation is not optional. It is guaranteed. This is why the loudest sound is not something you can engineer your way around. You cannot design a clever waveform to evade the limit. Any sufficiently intense disturbance will self-focus into discontinuity. The universe does not need a safety rule. The equations enforce it automatically. In this regime, the meaningful quantity is no longer pressure, but invariance across shocks. Rankine-Huguenot conditions replace wave equations. These conditions describe what must be conserved when smooth evolution fails: mass, momentum, energy. Everything else, phase, frequency, pitch, is discarded. That is a brutal filtering of reality. Loud sound erases detail and preserves only what conservation demands. In relativistic fluid dynamics, shocks are surfaces where the stress-energy tensor jumps discontinuously. These jumps must obey causality constraints. Entropy must increase and signal propagation must remain subluminal. This imposes absolute bounds on how sharp and energetic any sound-like disturbance can be, regardless of medium. Here, the loudest sound is constrained not by air, water, or solids, but by the structure of space-time itself. There is an advanced and rarely discussed parallel with the maximum force principle in theoretical physics. Some approaches to quantum gravity suggest that nature enforces an upper bound on force or stress. Loud sound is stress propagation. When stress exceeds what space-time matter systems can sustain coherently, geometry itself becomes involved. The disturbance is no longer a wave in matter, it is a redistribution of space-time curvature. Sound does not break this limit, it hands off responsibility to gravity. Sound is a Goldstone mode. It exists because continuous symmetries are broken, specifically translational symmetry in matter. Goldstone modes are fragile. They exist only as long as symmetry breaking is gentle. Push too hard, and symmetry restoration or further symmetry breaking occurs. The loudest sound marks the collapse of the symmetry that allowed sound to exist. So the limit is not mechanical, it is symmetry theoretic.
At extremely high energy densities, the notion of a medium itself dissolves. Degrees of freedom reorganize. What was once matter becomes a strongly coupled system with no clear quasiparticles. Sound relies on quasiparticles, phonons. When quasiparticles cease to be long-lived, sound ceases to exist as a concept. This is why in quark-gluon plasma, collective modes exist but are heavily damped. There is motion, pressure, stress, but no sound in the everyday sense. Loudness loses meaning before motion does. From an information-theoretic perspective, sound is a low-entropy encoding of energy transport. Shocks are high-entropy encodings. The loudest sound corresponds to the maximum rate at which low-entropy structure can be transported through matter before it irreversibly thermalizes. This is an entropy flux limit. And that connects sound to the same logic that governs black holes, thermal radiation, and the limits of computation. At the deepest layer, sound exists because the universe allows small departures from equilibrium. That permission is extraordinary. Most physical systems, when disturbed, do not oscillate, they decay. Sound is special because matter agrees to store energy briefly and give it back. Compression promises to undo itself. Rarefaction promises to heal. Oscillation is a pact between force and forgiveness. The loudest sound limit is the moment that pact is broken. When the disturbance becomes too intense, matter stops negotiating. It stops promising to return. The universe withdraws the privilege of oscillation and replaces it with something harsher: dissipation, fracture, heat, entropy. This is not punishment, it is inevitability. There is a quiet unity here with other ultimate limits in physics. Maximum temperature arises when adding energy no longer raises heat, but creates new degrees of freedom. Maximum force appears when stress reshapes geometry instead of matter. The loudest sound belongs to the same family of limits, not numerical ceilings, but conceptual transitions. Each limit marks the place where a description stops being valid, not because reality ends, but because it becomes richer than the description can carry. Sound is no exception. What feels most unsettling is that the universe does not prevent extremes by resistance alone. It prevents them by changing identity. Loud sound does not get louder, it becomes shock. Shock does not get sharper, it becomes transformation. Transformation does not get stronger, it becomes a new phase of matter, a new geometry, a new regime of law. Nature never says no, it says not like this. So when we ask, what is the loudest sound the universe allows? The most honest answer is not a number in decibels. It is this: the loudest sound is the final moment when matter still agrees to vibrate instead of surrendering to rupture. Beyond that moment, sound is no longer how the universe speaks. Conclusion. Sound feels fleeting, a whisper that vanishes as soon as it is made. But at its limit, sound reveals something permanent, the structure of restraint built into reality itself. There is no infinite loudness, not because the universe is fragile, but because it is layered. Oscillation gives way to shock. Shock gives way to change, and change replaces repetition. The universe does not scream forever. It transforms and moves on.